Let's examine one particular approach to reinforcement learning, known as Markov decision processes. Let's say you want to get a robot from point A to point B, and you want to penalize the robot for either accidentally crushing a human being or by falling off a cliff along its way. The problem is, the robot doesn't always make perfect moves. You can program in perfect moves, but movement is unpredictable. It occasionally makes mistakes. What can you do? To make this example more complete, let's take a look at Gridworld. Let's give everything probabilities of desired and undesired movements, and also give everything a score. If you maximize this score, your desired behavior will emerge. Let's also build in some living reward or living penalty. Adding some minor penalty for time will encourage the robot to find a more efficient route. Put a big reward at the end, and run some calculations to maximize your score. So again, why calculate probabilities? In a deterministic world, everything would simply work perfectly every single time. In the real world, there are very random or stochastic events, no matter how unlikely they are. The robot should have a huge negative penalty if the robot arm bumps into something. The robot will automatically avoid pathways that could even lead to this possibility. If the robot has a probability of falling, it makes the robot more cautious. So the goal is to maximize the average sum of its rewards that it can maintain. What if the robot becomes too cautious? Again, you counter this with a living penalty or an idea known as discounting. Make the robot more aggressive, you drive it to find a fast and hard solution. Markov decision processes are used to solve these type of problems. They have applications in robotics, economics, manufacturing, and voice dictation. There is no memory or no history. They combine statistical unpredictability and make decisions only based on data within the current state. Another name for an MDP is a policy map. A policy can be thought of as a pathway that the robot should take when on a factory floor. What if you have a problem or an issue or a challenge that runs continuously and it lasts forever? Do you continue and get infinite rewards? How do you calculate infinite rewards? Even worse, what if you have two different pathways and one pathway offers infinite rewards and the other pathway offers infinite rewards? Which pathway do you choose? There are three solutions to this problem. You could either only look a certain distance in the future, or you can use discounting. Make more current, closer rewards worth more than rewards further away. You also can just program in some final state, some final conclusion when the machine will simply stop. Discounting is usually the best of these three methods. It makes you aim for the close goals that you can get quickly and puts less of a pull on the distance goals. Again, it does this by making future values worth less than immediate goals. You want the solution, you want the goal that you can grab quickly and easily. It does this through the reward being exponentially decayed. If you have a discount rate of 0.9, then any goals you can grab immediately are worth full value. Goals that are one step away have a value of 0.9 times their value. If it's 2 steps away, it's 0.81 times its value. 3 steps, 0.73, 4 steps, 0.66, etc. Now you can combine discounting with a living penalty. Every move that the robot makes will take a flat subtraction of their score. This makes the robot want to do something more urgently. Now the robot makes the decision of what move to make based on what square this is. -1 is the fire pit, it loses the game. +1 is the gemstone. All of these arrows represent decisions that are done in order to maximize their score. The only difference between these four charts is the living penalty. Tweaking these two factors can produce drastically different behavior. The robot can become fearful or jump into the pit to commit suicide, or repeatedly bang into a wall, or make more reasonable choices. Look at the top left. The robot is always going to run away, even run into walls to avoid the fire pit. Why would it do this? It might waste a lot of time running into a wall, but you can only randomly slip off to the left or to the right. You can never accidentally slip backwards. So eventually, you'll slip off to the left or to the right and be able to make it to safety. Now, the top right is more reasonable. It risks going forward next to the fire pit, But in other words, it will take the long way around in other cases for safety. The bottom left, it will take moderate risks. It'll take the shortcuts. The bottom right, the living penalty is so huge, it's worse jumping into the pit. It's safer to end the game, jump into the pit, than trying to stay alive and get to the goal. Okay, so how do you make judgment calls? By making only a few relatively simple calculations with only a few variables. Your goal is to calculate the value of each possible transition out of the state based on the utility of that transition. What is the highest possible sum of all the discounted rewards that can be earned by making that transition? You then fill in the policy map. The optimum policy is the best pathway that starts from a particular state. The value of a transition, or a Q state, is the discounted value of the state that it is going to transition to, and the value of a state is equivalent to the value of the best possible transition that leads out of that state. This is somewhat of a circular definition, but it is generally solvable. What does it mean to have a value of 0.49 at the bottom left? A lot of factors are baked into this value. The living penalty, discounting, the probability of falling to the fire pit, the probability of success. All these factors are averaged to produce this number. The numbers represent that you actually try to act optimally in every single step to get to the best possible future state. The optimum policy is then shown by the arrows, showing the pathway from any state to the ideal goal state that you want. This chart has a noise or chance of random movements of 0.2, discount rate of 0.9, and no living penalty. Here is the chart of Q states or possible transition values. Since there are 4 possible directional moves, each triangle represents a different transition out of that particular square. Look at the one tricky state, where there's a red negative 0.6 value when going into the fire pit. This is interesting because it is being on the ledge and going into the pit. If you're committed to jumping into the pit, it's not 1, because there's a chance of still messing up and sliding off to the left or to the right. The state values can be determined from this chart by taking the highest possible Q value within each square. And you can also decide what is the optimum move by looking at the 4 Q values and choosing the highest value transition. What if you add a large living penalty on top of a large discount? Then suddenly more distant values become more sketchy. Same thing can be seen here when looking at Q values. So as you can see, experimenting with ideal values to create the best policy map becomes more of an empirical experimentation rather than an exact science. Exact calculations of these values are determined by Bellman equations, which again calculate exactly how to act optimally. Another important distinction here: rewards are the benefit or the cost of making exactly one move. The utility value is the calculation of all of the values from this point onward, from that point to the end of the simulation, which may be forever, as long as you act optimally. For one single step, you write a expect-max reoccurrence equation. To calculate actual or final values, you must use a recursive procedure or an iterative program that continues to calculate these values until they stabilize. Let's look at a totally different example, an AI simulation of a race car. How fast can you push the engine without blowing it out by using the formula on the previous slide? You have 2 different actions: slow, which is worth 1 point, and fast, which is worth 2 points. 3 different states: engine cool, warm, and overheated. The probabilities of changing state are not always a guarantee. 100% of the time when the car is cool and you go slow, you return to the cool state. But 50% of the time when the engine is cool and you go fast, you might go into the warm state, or else you return to the cool state. Vice versa, when you're in the warm state and you go slow, 50% of the time your engine may cool off or may remain the same. But 100% of the time, if you race the engine when the engine is already warm, you will blow out the engine. Let's show a demonstration of a top-down calculation of this problem. Starting with time 0, fill all values with 0. No points have been earned at all. At time 1, you can look at the blue side, run this equation by considering in two actions. Either go fast, gives you 2 points, 2 plus 0 is 2, or go slow, 1 plus 0 is 1. Fast is better, so let's choose value 2. On the red side, you can go fast, which gives you negative 10 plus 0, or go slow, which is 1 plus 0. So going slow is better with a value of 1. Overheated has no values or actions under any circumstance, so it always has a value of 0. Next step, look at time of 2. You can either go slow and then act optimally. That means you have a 1 plus 2 100% of the time, gives you a value of 3. Or if you go fast, that gives you a value of immediate of 2, but then you have a 1 50% of the time and a 2 50% of the time. This averages out to a value of 3.5. So the optimum choice in this case is to go fast because the future choices are better. For the red state, you have also two options. You can go slow and then act optimally. That gives you a plus 1, and then you're in the same state where you have 1 50% of the time or 2 50% of the time. This gives you a value of 2.5. Or go fast, which again gives you negative 10. So your optimum choice in this state is the 2.5, going slow. Notice that higher we are in the tree, higher the rewards are, because we have more time to get greater rewards for an infinite simulator. Obviously the score is always higher in the cool state, because your car will naturally do better in a cool state. Remember reoccurrence equations? You can examine these numbers and figure out the optimum policy, which is alternately go fast and then go slow. Choose going fast if the engine is cool, go slow if the engine is hot. If you keep up this pattern, you'll maximize the rewards. There is one big problem here, because in this particular case we have no discount policy to minimize future rewards. There's no convergence. No matter what choices you make, these values will continue to get higher and higher indefinitely. This is known as an expect-to-max tree, and it can be extended indefinitely for a never-ending race. We don't solve all of the values for all possible branches seen in the previous slides. We only explore the 4 useful values. If you implement this in the real world, as you make choices, branches of the tree are trimmed off. New branches explore up to a certain depth. We also don't have to compute an infinite number of levels down this tree. We can limit our depth by our computations by implementing a discounting factor to reduce the influence of the lower levels. This will also help us find a base level. Again, if there is a discount, there will be convergence, and at some point the influence will be so small that all points below that level are effectively 0. Based on the size of the discounting value, you can calculate the maximum level where the values become irrelevant, and literally set all values at that level to 0. For example, let's say you have a discount of 0.9. Assuming 15 levels of depth, you do 0.9 to the 15th power means you have an influence of 0.2. At 35 levels, the discount is 0.02. So if the 0.02 is close enough to 0 in your case, you can set level 35 as the base level, and instead of calculating down the tree, calculate up the tree. This idea of calculating up the tree instead of down is known as value iteration. You use these values to solve the problems from the bottom up. The base is either the goal states, such as the gemstone or the fire pit, or the base is the point where the future rewards are so small they can be assumed to be 0. You build the pathway from the far future back up until the present. There are many mathematical approaches to solve these types of game tree problems. Using these formulas or looking at value iteration is not always the best solution. It's very slow. It looks at way too many possibilities. It examines branches that probably won't be picked. It's considering every possible action every time, and this is way too many possible actions. The policy, or the arrows as seen in the previous case, tend to stabilize long before these numbers stabilize. Another approach is known as policy iteration. In simple English, this looks at the arrows as they converge. Initially they change a lot, later they change hardly at all. Back to Gridworld. Note how the policy, or the arrows, are developed from the two goal states, backwards to the start state. The policy itself may undergo additional refinement and modification as the values change, but after only 12 iterations, the policy itself is stable, and no further changes take place to the arrows in this chart. Between 12 iterations and 100 iterations, the values continue to be modified, but again the policy itself is stable and finalized. These ideas are a few of the basic concepts behind reinforcement learning, and can be used to solve problems such as controlling robot motion, and of course more interesting challenges such as beating Mario Brothers, Pac-Man, and of course Flappy Bird. Thanks for listening.